I welcome all of you to the class. As far as today's class is concerned, today we will be doing some numerical problems to consolidate on the concepts which we have already discussed. We will begin with an example 1.8 from our textbook. The example 1.8 says the member AC as shown in figure 1.18 is subjected to a vertical force of 3 kilonewton. Okay, so we are having the member is AC, which is subjected to a vertical force of 3 kilonewton. Determine the position X of this force so that the average compressive strength at the smooth support C is equal to the average tensile strength in the tie rod AB. The rod has a cross-sectional area of 400 mm square and the contact area at C is 650 mm square. As far as the question is concerned, the question is like we have the rod, the member is AC, fine, we are having the member AC. Okay, as far as the member AC is concerned, the member AC is subject to a normal load of 3 kilonewton, which is trying to move the rod AB in the downward direction. The tendency of this 3 kilonewton rod will be to move this member AC downwards. But at end A of the member AC, we are tying a rod. Rod is AB. Okay. So at end A, we are tying up a rod AB. Okay. So because of this rod AB, the rod AB is preventing the member AC from falling down. So if you don't have, if we do not have the rod AB, so what will happen to the member AC? The member AC will simply fall down. So it's because of this rod AB, I mean to say this rod AB, it's because of this rod AB that this member is being prevented from failure, is being prevented from falling down. Now the question says that the area of the rod AB is given. Fine. The area at C is also given to us. Okay. It says whatever is the stress generated in the rod AB, that stress is equal to the stress generated at point C. Okay, whatever is the stress generated at area at point C, the same is the stress generated in the rod AB. So how much is the distance X? For getting me or not? So how we will solve this question? Um, Let me draw the first of all, we'll begin with the free body diagram as is given on the left hand side of this, as is given on the left hand side. As far as the 3 kilonewton load is concerned, what will this 3 kilonewton load try to do? This 3 kilonewton load is trying to move the section AC in the downward direction. Okay. So as far as the end C is concerned, at end C, there will be a reaction, and that reaction at end C, we will call that as RC, will be in the upward direction. The reason is simple. The reason is because this 3 kilonewton load will have tendency, this is a support here. Okay, let me write here, this is a support, this is a support. Why do we have a support at C? Do we have a support at C? If we don't have a support at C, okay, then what will happen to the structure HC? What will happen to the member AC? The member AC will simply fall down. Okay, so as far as the support at C is concerned, the support at C is providing the necessary reaction, that is nullifying the effect of this 3 kilonewton load in moving this member AC downwards. So it means the reaction at C has to be in the upward direction. Even if you cannot make it physically, what is the direction of the reaction C? Give it any direction. Okay, we are free enough. So some of you, if you are not able to make it how the reaction is in the upward direction, you can assume let the reaction be in the downward direction. Okay, because once you write the equilibrium equations, the equilibrium equation will automatically correct the direction of your reaction C, which I will show you later on. Okay, so let's first of all, what we are doing, we are first of all saying let at and C, let at C the reaction be equal to RC. RC is the reaction at and C, which is actually nullifying the effect of this 3 kilonewton load. Number one. Number two, this 3 kilonewton load again is trying to move the member AC in the downward direction. Okay, so the action of this 3 kilonewton load is being nullified by the rod AB. Okay, this rod AB will try to move this member AC in the upward direction. That is, the reaction at in the rod AB will be, we will let's call this as RB. Okay, let's call this as reaction in the rod AB, or I will call this as RAB to make it clear. Let's call this as reaction AB. Fine. This reaction AB is produced in the support AB, okay, against the effect produced by the 3 kilonewton load. It's very simple. If you do not have the rod AB, then what will happen? This point A will simply move down, okay, or the member AC will simply move down. But the effect is being nullified by some reaction produced in the member AB. That is only possible when the reaction will be in the upward direction. Let's call that as RAB. That's what we have done. So what we have done, at end A, we are drawing the free body diagram. We have the reaction in the upward direction as RAB or FAB. You are free enough to change it. You can call it as FAB or RAB, whatever you have, whatever you want. And at end C, you have RC or FC. You are free enough to write it. So first step is, so I can write here, whenever you are analyzing for the stresses or the strains, the first step will be draw the free body diagram. Draw free body diagram. Draw free body diagram. And the question is, why do we draw the free body diagram? We draw the free body diagram to see or to analyze the stresses which are created, to analyze the forces which are in our member. Okay, the free body diagram gives us the forces, number one. Number two is, once you write the free body diagram, write down the equilibrium equation. Write down the equation of equilibrium. Write down the equilibrium equations. What are the equilibrium equations? You look at the structure. Okay, this structure is in equilibrium. It's neither moving up nor moving down. It's neither going up nor going down, neither going right nor going left. Fine. It means if you treat this to be your x-axis and if we treat this to be our y-axis, then we can write summation of all the forces along x-axis should be equal to 0, as well as summation of all the forces along y-axis should also be equal 0. Fine. There is no force acting along x-axis on this member, so this automatically is 0. But let's calculate the forces acting along y-axis. So along positive y-axis, we have FAB or RAB. So I will write this as FAB, positive, because it's acting along positive y-axis. We're having a force of 3 kilonewton acting in negative y-axis. So I will write this as minus 3 kilonewton. And we're having FC acting along positive y-axis, so we'll write this as FC. There is no other force acting along y-axis, and the system is in equilibrium. Summation of all these forces has to be equal 0. Therefore, from this we can write, therefore from this equation we can write FAB plus FC is equal 3 kilonewton. Fine. Let me call this as equation number 1. Fine. Now, since this system is in equilibrium, we have done it in engineering mechanics, fundamentals of mechanics, that for equilibrium, it's not only the summation of forces that should be equal to 0, but summation of all the moments should also be equal to 0 for the equilibrium. Okay, the system should not even rotate for the system to be in equilibrium. So if we start taking the reaction, sorry, if we start calculating the moment, select a particular point. Okay, let's select this point A. Okay, and imagine an axis passing through point A. Okay, imagine an axis passing through point A. So if you treat this to be your x-axis, we treat this to be our y-axis, and we treat this to be our z-axis. Let's call this as zz prime. Okay, is an axis passing through point A. So we will calculate moments about an axis, calculate moments about an axis passing through, about an axis. I will write this as zz prime passing through point A. Fine. passing through point A. Calculate the moments about an axis ZZ prime passing through point A. Fine. So first and foremost, we will calculate the moment about of the force FAB. The moment of the force FAB about point A will be zero, because we know whenever you have to calculate the moments, this is what we have done in engineering mechanics. If you have force F acting here, okay, so if you are calculating the moments about an axis passing through point A and this distance is x, then the moment will be F into x. Fine. Whether positive or negative, that's the secondary question. But moment is force into force arm. Fine. But look here, when this F matches with the axis passing through point A, when you translate this F to the point A, then the moment automatically becomes equal to zero, because your x becomes equal to zero. The same is the case. The moment of FAB about an axis passing through point A will be equal to zero. We need not to take the moment of this force. Now there will be the moment of this 3 kilonewton force. The moment will be, so we'll write summation of all the moments about an axis passing through point A for equilibrium should be equal to zero. Fine. So first moment will be, because of this 3 kilonewton load, we'll write this as 3 kilonewton, okay, multiplied by the force arm, that's x. And this 3 kilonewton load is trying to rotate your beam in the clockwise direction. We will take this moment as negative, okay. The second moment will be because of this FC. FC is trying to rotate our beam in the anti-clockwise direction. It's trying to rotate our member AC in the anti-clockwise direction. Its moment will take as positive. So it will be FC multiplied by 200 mm. Convert mm into meter. So it will be 200 by 1000 meter. Okay. This should be equal 0. Fine. Okay. So let me write few more steps here on the left hand side. I can write now. Let me take it over here. I can write here FC multiplied by 0.2 is equal 3 kilonewton multiplied by x. Our force is in kilonewton, our distance is in meter. Fine. So FC becomes equal 3 kilonewton into x divided by 0.2. So this is the value of our FC in terms of x. I'll call this as equation number 2. Fine. This is equation 1 and this is equation 2. Fine. So now the given condition is that the stress generated in the rod AB is equal to stress generated at the support C. The stresses are same. Now look here, as far as the free body diagram is concerned, in the rod AB, the load is in this direction and you have area in this direction. Okay. So if you draw the area, if you see the area is like this and the force acting is like this. So you see your area and your force. If you draw the area vector even, okay, your area vector and the force vector, area vector and the force vector are parallel. Therefore, the stress generated here will be the normal stress. The stress generated here will be the normal stress. The same is the case here. Fine. So what we will write, we'll write here, we'll equate the normal stresses at both the ends. We'll write normal stress in the rod AB. This is given to us. Okay. We'll write normal stress in the rod AB is equal. This is a given condition. Normal stress at end C. So how much is the normal stress in the rod AB? That will be force in the rod AB divided by area of the rod AB is equal the force stress in the rod C, that is end C, that is force at end C divided by area at C. Fine. Therefore we can write, okay, therefore we can write FAB. Okay, so we have FAB. I will write FAB divided by area at end B. Okay, area at end B is equal to how much? it's equal to 400 mm square. We can do one thing here. If you recall, we have divided it by 1000 to convert our mm into meter. Since we have area in terms of mm, no need to convert your mm into meters. Fine, this will make it quite easy. So what we can do here, we will not divide it by 1000. We'll keep at fc is equal to 200 mm. Okay, this is in mm now, so it will become 2 divided by 200. Just make this correction here, and this will be fc is 3 kilonewton divided by 200. This is 200 mm here. X is also in mm. Okay, so this is 200 mm. Our units of distance are in mm, so x will also be in terms of mm. Fine. So when we measure x in mm, okay, mm will cancel, so we will have only one unit, that is 3 kilonewton. Fine. Now area at AB, area of AB is given as, the rod has a cross-sectional area of 400 mm square. So I will write this as 400 mm square is equal to FC. Okay, so I can write this as FC divided by, fine, FC divided by area of C, that is 650 mm square. So mm square and mm square cancels. Okay, so we can write 650 divided by 400, force in AB is equal to FC. Fine. Let's call this as equation 3. Let's call this as equation 3. Fine. We have to find the value of this x. How much is the value of this x? Fine. So what we can do now, let me clear some space. Let me clean this. I will only be dealing with 3 equations. Okay, so now I have 3 equations. We have FAB plus FC equal to 3 kilonewton. This is our equation 1. That is this. Let me, okay. And our second equation is 650 divided by 400. That's equal 650 divided by 400 is 1.625. So I will write this as FC is equal 1.625 FAB. So I will be just solving these 2 equations, which are quite easy now. Okay, so we can, let me clean this as well. So what we can write now, okay, substituting the value of FC in equation this. Okay, so we can write this FAB plus FC, that's equal 1.625 FAB is equal to 3 kilonewton. Fine. So 1.625 FAB plus FAB is 2.625 FAB is equal to 3 kilonewton. Can't we find the value of FAB? Therefore, FAB becomes equal to 3 kilonewton divided by 2.625. 3 divided by 2.625. That's equal to 1.143. So FAB becomes 1.143 kilonewton. This is the value of FAB. Fine. This is the value of our FAB. But we already know how much is the value of FAB and FAC? That is 3 kilonewton. Okay, if we substitute the value of FAB, we'll get the value of FC. But we know FAB plus Fc is equal 3 kilonewton. Fine. FAB we know, therefore Fc becomes equal 3 kilonewton minus FAB, that is 1.143 kilonewton. Fine. Therefore Fc is equal 3 minus 1.143. 3 minus 1.143, that's equal 1.857. That is 1.857 kilonewton. This is the value of our Fc. Fine. Now what we will do, we'll substitute the value of this Fc in this equation. Fine. That is, from this equation what we can obtain, Fc, that's equal 1.857 kilonewton is equal to 3 kilonewton. 3 kilonewton divided by 200 into x. Fine. So we can write this as kilonewton and kilonewton will cancel. So it will be 1.857 multiplied by 200 divided by 3 is equal to x. And we have already taken x in mm, therefore this answer will be in mm. That is equal, x becomes equal 1.857 multiplied by 200, that is 371.4 divided by 3, that's equal 123.8, that is 123.8 mm. The value of x is approximately, this is 124 mm. This is the value of the x where we should apply. Okay, so this is the value of the x. Now let's see what the book is giving us as the answer. So if I look at the book, the value of x from the book is, see here, it's here. Let me re-annotate the terms. The value of x is here. It's here. It's 124 mm. 124 mm. This is the same answer that we have obtained. Fine. This is how these questions need to be solved. Let's solve one more problem. Now let's go to the problem 2. Let's suppose we are having, the question is, we have a bar like this. There's a bar. Very thin bar. And this very thin bar is supported on, is being supported here. It's supported here. And it's supported here. Fine. Let me call this as end A. This is end B. Fine. Now let me assume this is massless, which is quite academical to assume. This is massless. It does not have a weight. Okay, it does not have a mass. And let me suppose at the midpoint we are applying a force F. Fine. We're applying a force F such that the total span, what you call as the total length, this is called the total span. The total span of this bar is L. Okay, what we call as a length, this is also called as a span. We say the total span is L, fine, total length. At this end, we say the area of cross section here, the area of cross section here is, say for example, A1, and the area of cross section here is, say for example, A2. The area of cross section here is, say for example, A2. Fine. The question says, for this rod of span L subjected to force F at, say for example, the distance of the force from this end is, say for example, this distance is L by 2, half of the length. Half of the length. The question says first, the question says calculate.
सर रिपीट कीजिए सर.
We have, the question says that we have a rod AB of span equal to L, that is of length equal L. We're applying a force F on this rod AB at a distance L by 2 from end A. That is the distance from end A to this force F is equal to L by 2. Fine. At this end, at this support, the area of the support is A1. Okay. And the area of this support is, say, for example, A2. We are asked to calculate how much is the, calculate first stress in area A1, and second is calculate stress in area A2. How much is the stress at this area? How much is the stress at this area, and how much is the stress at this area? Cross sectional area. Okay, these are, I should write here, these are cross sectional areas. These are cross sectional areas. This as well as this one is also the cross sectional area. Cross sectional area. So first of all, whenever you have these types of questions, first of all, draw the free body diagram. Free body diagram, you can replace this entire diagram by a simple bar like this. It is supported at end A. It is supported at end B. And it is supported at end B. I will write this as like, and you know, what is the function of these supports? The function of these supports, support at A, support this support 1 and support 2, is to support it. I mean to say, if you do not have these supports, if you take out the support at 1, if you take the support 2, what will happen to the rod AB? This rod AB will simply fall down. Okay. The force F is trying to move the rod in the downward direction, but this rod is not going in the downward direction. It means the support A and support B, they are producing the reactions that are nullifying the effect of this force F. Okay. So it means this force F is pushing this support in the downward direction. In response to that, the support will produce the reaction on the rod in the upward direction. So we write there, this is reaction at A. Same is the case at B. The force F on the rod is trying to push this support B in the downward direction. Therefore, the reaction will be offered by the support 2 on the rod in the upward direction. Therefore, on the rod AB, we will be having reaction at B, RB. So we always replace the supports by the arrows and these slashed lines. It means you have supports. Fine. Apart from this, at a distance L by 2, there is force F, such that this distance is given to us as L by 2. Fine. While as the total span is equal L. Okay. Now this question becomes quite comfortable for us. How? What I will do? Well, this is the free body diagram. This is what I was telling you in this previous step. This is your step number 1. So after drawing, so this is our step 1. This is step 1. That is drawing the free body, drawing the free body diagram. This is what we have done. Okay. After drawing the free body diagram, the step 2 is write, step 2 is write the equations of equilibrium. Write equations of equilibrium. How do we write the equations of equilibrium? First is summation of all the forces should be equal to 0. Since there is no force acting along x-axis, there are only forces acting along y-axis. Okay, so we'll write Ra is acting along positive y-axis. We'll write this as Ra. Rb is acting along positive y-axis. We'll write this as Rb. F is acting along negative y-axis. We'll write this as minus F, has to be equal 0. Therefore, we'll write Ra plus Rb has to be equal F. We'll call this as equation number 1. Fine. After this, I just said that the equilibrium does not mean the summation of forces has to be equal to zero, but summation of all the moments about any point should also be equal to zero. Okay, for our ease, we will be taking the moments about point A, about an axis passing through point A. Though you are free enough, you can take this point C, you can take an moments about an axis passing through point C. You can take moments about an axis passing through point B. The students are free to take the moments, but be careful. As far as the system is, as long as the system is in equilibrium, summation of the moments about the selected point has to be equal to zero. So when we write summation of all the moments about an axis passing through point A has to be equal to zero, there will be no moment because of RA, because RA is intersecting with the axis about which we have to find the moments. So there will be the first moment because of F. The moment will be F multiplied by the force arm, that is L by 2. And look, this F is trying to rotate the rod AB in which direction? It is tending to move the rod AB in this direction, that is in the clockwise direction. We'll write this as minus. Now look at RB. RB is trying to move the rod in the upward direction. If that happens, then what will happen? The rod will go like this. It will have the anti-clockwise angle, which we take as positive. Fine. That will be RB multiplied by L. Fine. This summation has to be equal to 0. F will be given to us. Okay. So what we will write, RB into L is equal to FL divided by 2. L and L cancels. We write therefore RB becomes equal to F by 2. This is the value of RB. The reaction at B is equal to half of the force applied. Similarly, since we know RA plus RB is equal to F in working, since we know RA plus RB is equal to F, therefore RA becomes equal to F minus RB. RB is equal to F by 2. So it is F minus F by 2, that's equal to F by 2. What is this? Your RA is also equal to F by 2. So let me uh, clear some space and see what we have obtained. We have obtained RB RA is equal to RB is equal to F by 2. Fine. Now how much will be stress at A? Stress at A will be equal to force at A, that is F by 2, divided by area of A, that is A1. Okay. How much will be the stress at B? Stress at B will be equal to the force at B, that is RB, isn't it? The reaction that is acting at B is RB, that is F by 2 divided by area, that is A2, which I was saying force at A is equal RA divided by area at A, that is A1, and stress at B is equal reaction at B divided by area at B, that is A2. Okay, this is how we have to solve these questions. Whenever you have these types of questions, you have to write the equilibrium equation, summation of all the forces and the summation of all the moments. Fine. Based on this, if you have a question like this, we have a rod or a beam AB. Its length is, say for example, 100 meter. At the center of this rod, we are applying a force of, say for example, 10 kilonewton. Okay, this distance is half, this is 50 meter. This distance is 50 meter. How much is reaction at A? How much is RA? How much is RB? I just told you RA is equal to F by 2, that is 10 kilonewton divided by 2, that is equal to 5 kilonewton. And RB is also equal to F by 2, that is 10 kilonewton divided by 2, that is 5 kilonewton. This is one thing. Second is, if at support A we are given the area, it's like this. We have a support here. Fine. We also have a support here. If we are given the cross-sectional area, if we are given this cross-sectional area, how much will be the stress? Stress will be 5 kilonewton divided by the given area. Let me call that as A1. Similarly, you can do it for support 2. This is how these types of questions are to be solved. In the same way, if you have a question like this, which we will be doing in the next class, if we have a question like this, say for example, it is support A, support B, and say for example, it is subjected to a uniformly distributed load. Fine. These types of questions, hopefully, we'll be taking in the next class. Thank you very much.